about UNets, and we will wrap up with the UNet and a few kind of evaluation measures that I will mention. And there are lots of things to explore in terms of evaluating the quality of the generated data, and it's an ongoing area of research. Now we're going to look at a new kind of, or a different kind of an encoder network, which is the UNet. So if you guys have taken any course in deep learning, you may have learned about, UNets and how they work. So here, the idea is actually very simple. What I explained earlier, that we do have an encoder and decoder network. So here in this case, we have an encoder-decoder network. We have an input GraphGS and output GraphGT. So a UNet is an autoencoder, which means it's a self-supervised model. So what it does, it takes here the Graph UNet was first proposed in 2019, which extends the UNet model. So it extends the UNet model to graphs. All right. So first we have, it's a self-reconstruction problem, which means you have, for example, the G here, and you reconstruct it through the decoding, and the goal is to minimize the distance between G and G tilde, the reconstructed data. So it's a self-reconstruction loss. So here, self-reconstruction loss, okay, or self-generation loss. So why this is important? It's important because when we do the encoding, so this is the encoding here. So when we do the encoding process, we will learn the embedding of the graph. So we'll learn a very compact representation of the graph at this level in the embedding space. So this is the latent embedding space. So in a typical UNet, we don't constrain the embedding to follow a normal distribution. So here it's actually based on the data that we're having, based on the training sample that we have, G1 to, for example, GN. Or big N here, okay? So it's data driven or data dependent, and there are lots of variations. But anyway, so the idea is that we want to encode this graph. By encoding this graph through this, through these layers right here that we're going to go over quickly, we will learn an embedding, and by learning that representation of the graph, we can then decode it back and reconstruct the graph itself. Okay, so here we want to minimize between the reconstructed graph by the decoder of the embedding, or the learned representation in the latent embedding space, and then and versus the ground truth original one. All right, so it's an encoder-decoder network, and what it has different operations. It's composed of different operations. So the first one we have learned, so we know what the GCN is. We're just doing node embeddings here. We're updating these node embeddings based on a message propagation rule, or the update rule for the embeddings that we use with attentioner. There are different variations we have seen, okay? So we have different GCN layers. You can see them here in the graph, right? And then we have additional operations. So we have an operation that is graph pooling, or G-pool. So we're pooling twice. After each GCN layer, we're doing G-pool. And in the decoder, after each GCN layer, we're doing an unpooling, graph unpooling. So we're unpooling here. So what we're going to learn now is how these pooling and unpooling layers work. And in CNNs, it's basically sampling, downsampling, and upsampling. So how to downsample a graph and how to upsample a graph. And this is what they have introduced in the paper. So they're trying to define parallels to these downsampling and upsampling techniques. So a graph pooling is actually you downsample somehow, downsample. All right, and here the unpooling, you upsample. Okay, so yeah, so this is the view of a UNet. We call it a UNet because it has this kind of shape, a U shape, right? And here we add the skip connection. So these skip connections have been introduced in UNets, and then we have also residual networks with the residual connections. And so, yeah, so these are basically, they recall the original feature maps. They do concatenation, but we're not going to go into these details. But let's look at the most important part here. So we know what a graph convolutional network or layer is. Now let's look at how we're downsampling in the encoding process using gpool, and how we are upsampling in the decoder function using unpool, gunpool. So first, for the proposed graph pooling, so here it's actually very simple. So if you guys look at this block, you can easily follow the mathematics. You can derive these equations by yourself. So I'm not going to go over them in detail. So these are beautifully explained in the figure. And in the figure, here in the figure caption, they take, a 4x5 matrix, and 4 is the number of nodes, 5 is the number of features. So these are the features, right? And you have nodes here. So, okay, so what they're doing here, they're trying to pull to do the graph pooling. And as you guys can see in the graph pooling, we started with a graph that has many nodes, and we ended with a graph that has only 2 nodes, right? So this is the pooled graph. So now, how are we going to do the G-pooling here to minimize sequentially, to go, for example, from 4 nodes to 2 nodes here. So here we went from this graph, right, to 4, and 4 with the G unpooling, we went, the G pooling, we went down to 2, etc., etc. Okay, so let's look at this example. So here, first, we take the matrix. So our goal is to reduce the number of nodes from 4 to 2 nodes. So here we have 2 nodes, right? And then we will have a 2x2 matrix. So originally, the adjacency matrix was 4x4 because we have 4 nodes. So we updated, we have pooled 2 matrices. We pooled the node feature matrix, right? So D here is the number of features, right? The size of the feature embedding. And we pulled also the graph topology. So we pulled both A and X. And this beautiful illustration, it follows these equations, all right? So first, what we do a projection of the matrix. So we learn a projection vector. So this vector right here, we will do a projection of every single node using this learnable vector. So we have a learnable vector P. So this is our learnable vector. And then we normalize it by the norm of P. So we divide all, like after we do the multiplication, we're going to have a representation for every single node. So we're going to have, for each node, we're going to have a value, right? 1, 0.2, 0.8, etc. So these are the number of nodes. So Y here, it belongs, so Y belongs to Rn, with n the number of nodes. We put n number of nodes, all right? So we have n values for every single node in the original graph. And this is a compact representation of the node that we obtained through the projection. So you projected every single node embedding, all right? So let's do it this way. Each node embedding is projected using a projection vector, or integrated using an information integration vector. So we have seen this. We have seen that the multiplication of a matrix and a vector has different meanings. We can call it diffusion, projection, information integration, right? So here in the paper, they call it projection. So it's a trainable vector that we're learning P, and it has 5 values. So we have 5, it has, yeah, so it's the dimension of the features. P belongs to RG, so D is the number of features. And then what we're going to have after this projection, we're going to get a compact representation of each node embedding. So the node embedding here is reduced into a single value over there, all right? Now, after that, what happens is that we're going to see that each node has a different value, embedding value, single value in this Y vector. So this is an embedding of all nodes. So single value. So next, the idea is that we want to select the nodes with the highest values. So we will select basically the nodes with the highest scores and record their indices in the top K node selection stage. So here, the top K we, for example, find that these two nodes have the highest value, 0.8 and 0.9. So we will mark them. So we will select these nodes. And now what we're going to do, we will find these nodes in the original XL matrix. So we will identify them. So we will retrieve their rows, the first node and the third. And we will construct, you know, our smaller matrix that has only these two nodes, right? So now we have only two nodes. The nodes that have the highest embedding value, the most important ones, we consider them as the most important ones, okay? So now we get the X tilde. X tilde here is basically a selection of rows in the original matrix. So we only retrieve these rows right here, okay? And we got them over there. So it's actually very easy. And then what we do an element-wise multiplication. So XL here has K times D, so it's K times D, all right? So K times D. The Y vector, our Y vector tilde is actually, we apply the, so how do we get that? So we apply the sigmoid to these two values. So here we're basically casting these into between 0 and 1 to make sure that we either select or not select, okay? So now we transform these values, so it will have K values. So here it's K times 1, and we multiply it. Actually here I should put, so they use C here for the number of, so I can put it here, K. So C here is equal to K. So this is the selected nodes, okay? So maybe they use a different notation, that's fine. So, and then we're gonna have, sorry, actually it's D, right? So let me just fix this. K is the selected node. C is actually the number of features, right? So this is the number of features, what we call D. So here D is equal to C is the features. So we transpose it. So this should belong to D times 1. So if we transpose 1 times D, and you guys can see that now we can do element-wise multiplication between these two matrices. So this one is basically this product right here by the transpose of 1 is to make sure that we're getting a matrix, and we can do element-wise multiplication for you know, the most important for weighting the most important features. Okay, so we do element-wise, element by element. And after doing that, we retrieve the matrix. So this is this will get us the final updated matrix XL plus 1 of the new pooled graph. And we do the same for A. So for A, it's so simple. We just retrieve the rows and using the indices. And we only keep, for example, here, we retrieve these nodes, right? So we only keep their connectivities. And we're going to get here an A 2 by 2, AL plus 1 2 by 2. And this will be the matrix of the retrieved graph. So these operations are actually very simple. You guys can go over them one by one again, but it shouldn't be difficult. And the idea is that we want, so the idea of this transformation is, this projection is we want to compactly learn how to weigh each node. And if we find, then we select the nodes with the highest weights, and then we will down sample or pool our graph, shrink our graph based on these most important nodes by selecting sequentially the most important nodes and the most important. So here, for example, we selected, let me find them. So these guys, so these are the most important nodes that we pulled. And then from these, actually we pulled only these two guys were pulled because these are most important, which are these ones, okay? So you can see that we're pulling, you know, different graphs, and then we're gonna reconstruct the graph. So this is the pooling process, and it's actually simple, and it obeys to these beautiful, you know, operations that have a good logic and rationale between behind them. Now, the last part is the graph pooling, which is the most simple part in a GUnit or GraphUnit. So remember, guys, now when we had the pooling in the encoder, now we want to do the unpooling. So first we unpool and we apply a GCN layer to update the nodes. So the idea is actually very simple. So let me actually take this copy, right, and then I'm going to paste it here. Oh, actually, it's right. Okay, so I don't need to do that. It's actually well illustrated in this example. So in this example, we did the pooling, right? So we did the pooling, and then we applied a GCN. And now we need to unpool. So to unpool is so simple. So basically here, what they propose is that the original graph has 7 nodes. So these 7 nodes are downsampled using the G-pool layer, resulting in a coarsened graph with 4 nodes. Okay. And position information of selected nodes. We have the index. We know which nodes have been selected in the index. Here the IDX. Okay, they are stored in the IDX vector, and then the corresponding G-unpool layer uses the position information to reconstruct the original graph structure by using empty feature vectors of the unselected node. So it's so simple. You go here, you know that these have been deleted, so you restore them back, but you put empty features. So remember, guys, we're learning how to embed the graph, so it's all about learning these embeddings. So here we put them, we put empty features, so all of them are zeros, right? And then what happens when I restore through the G-unpool, when we add the features of these nodes and reconnect them based on the matrix A. So A is fixed, of course, so we can easily reconnect, right? So we can restore the A also, right? Now, what we're going to do is apply a GCN layer, and this is the key idea. So once I restored these two guys, now I need to apply a GCN layer, and a GCN layer will update the embedding of these two nodes. Update. So this is the key. Sorry. So yeah, so this is the key idea, is that once we apply a GCN layer here, these values will change. They're not zeros anymore. They will be updated according to our propagation rule, the propagation rule that we'll use in our computational graph, et cetera, et cetera. So basically the idea is so simple, is to kind of put them back, put a bunch of zeros, right? So 0, 0, 0, 0, and then update them back through a GCN layer. And when you do that, actually, you're optimizing this loss. So an autoencoder, so I'll explain in a bit, we're optimizing a loss in such a way that all these GCNs and the G-pool, right, all of these will be optimized. So everything is optimized and learnable. And this is thanks to our loss function. So let's look at this. So actually, GraphVAE has been used in different generative tasks. So for example, here, it has been used in a graph super resolution network, GSR-net, published in 2018. So how can we use GraphVAE for super resolving graphs? So you guys can have a read at the paper, but you can also, you know, think about, now that I have reconstructed the same graph, which has, you know, 4 nodes. So this is the input brain graph. Now, how can I, you know, keep on unpooling until, you know, to super resolve? So add new edges and a node. So basically, you can think about a way of upgrading or extending, you know, GUnet or GraphVAE to, you know, generate not only, so once you have this generated properly, reconstructed properly, you can keep on upsampling or unpooling until you get, in a new way, of course, until you get a new graph. So there are different ways here, but you can see here, this is our UNet, and it's a self-supervised learning. So we have a reconstruction, a graph autoencoder block, but we can add maybe other blocks. Maybe add a new block for super resolution, okay? To make sure that we can increase the dimensionality of the nodes and the edges in the graph. Now, how to generate new graphs? So you may think, or you may say, okay, so now we have a graph autoencoder, we're just regenerating the same thing, but how can we generate a new graph using, you know, GraphVAE, for example? So this is a good question, and you may think about it. So let's first start with the problem that we're having. So we're having a graph here, okay? So this is our graph, and we want to reconstruct it. So in this case, let's say reconstruct the same graph. So ideally, it would be the same, all right? So let's call this graph GI, and this is graph GI tilde, reconstructed, all right? So okay, so maybe I'll call GI, and then, you know, ideally this will be close to paste, to this one. duplicate. All right. So to the ground truth GI, right? So this is the ground truth, but maybe we have some mistakes. We have made some mistakes. So maybe we added these two connections, right? And maybe we remove this one. Okay, so the prediction is not very, very good here, but still, you know, that's maybe our prediction here after training, self-reconstruction after training the network. So how do you train the network? First, we have, of course, you know, GCN, Gpool, right? So these have parameters. We have multiple layers, right? We kind of stack them. So let's call these operations. They have a theta. So here we're going to call this a theta parameter. So this is the total set of parameters. So we have F encoder, and it has parameters theta. All right, so it takes in GI and theta, and then it outputs ZI here. So this is our embedding of the graph. And then here we have an F decoder. Of course, we have GCN layers, and we have simple, you know, G unpool, which is not very learnable. I mean, this is not learnable, but let's call this also phi, the parameters of the decoder layers, all these layers, all the parameters. And here we go. So phi. All right. So now what is the final output? So how do we calculate GI tilde? So GI tilde is equal to this one. Okay. So the F decoder. So the F decoder actually here made a mistake, takes ZI. Okay. So it's F decoder, the embedding that we learned here, the graph embedding of graph GI, given the parameters phi. And let's say we have optimized these. So I'm going to put a star there. And now let's write it again. So I want to write it again. So here, what is ZI? So F decoder of, and I will rewrite ZI. ZI is actually equal, you guys see this diagram, is the output of F encoder. So it's F encoder of the original input graph GI, given the parameters theta, right? And then here, given the parameters phi star, and let's put star there. All right, so you can see it's a composition of two functions. So GI is F decoder of, you know, of F encoder, right, of GI, given all the parameters. All right, so we're composing two functions, and this is how we optimize. So now we can write our loss. So the loss, how do we write the loss function? So it's basically we want to minimize over theta and phi of this whole thing, okay? And let's make it small, minus the ground truth, okay? So this is actually GI tilde, the predicted one, and we can use different losses here, but this is an example of a loss to optimize. And as we optimize the set of parameters of the encoder and the decoder, as we optimize these, we are able to reconstruct the same graph very well, and these will be very close, so maybe we'll make less mistakes, all right? Now, let's go back to the question. What's our question? How to generate new graphs, okay? So you can take, for example, the embedding of this graph. So let's say this is graph GI. I take its embedding, ZI. So one idea is to perturb it a little bit. So I can add a small noise, an epsilon, right? So drawn from a prior distribution, P of epsilon, right? And then by adding this random noise with random values, I'm going to get a new Z. So let's call it Z, you know, I. You know, okay, so ZI, for example, I'm gonna call it a different one. So here, double indexing, okay, ZI1, all right? So this ZI1 is a vector. Now, what I can do is input this vector, pass this vector, do a forward pass of the vector through the decoder, and what it will give me basically a new graph. A completely new graph. So we're going to generate a new graph. And here will be the same number of nodes, probably because we have the same number of nodes, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and this is our graph, okay? So you can see that we have, generated a new graph, and hopefully this new graph will fit the distribution of the original data, and this is the distribution, for example, of the P data, the original data, and the red one is the generated data, okay? Generated data, all right, or generated graphs. So we can do the same here. So we can take, add another epsilon, another perturbation, and by adding another perturbation, we're gonna get Zi, for example, K, or P. So we'll have many perturbations, and we can have thousands and thousands of samples, created, and every time we pass this through the decoder, right? So this passes through the decoder. So F decode ZIP by star. So we're gonna get a new graph GIP predicted, and this will be a new graph that we predict. Okay, cool. So that's how we do generation here. And so now there's another question. So I want to ask before I show you the solution. So I want you guys to take a few minutes and think about this. And if you're watching the video, maybe you can pause. So how to generalize GraphVNet to a target graph with also edge attributes. So we want, let's say, we don't want to predict only the topology and, reconstruct the original features, like basically recover the same graph, right? So with its features and topology. So imagine if we have also edge features. So we're gonna have, for example, edge features right here. So all of these will have attributes. How can we, extend GraphVNet to accommodate edge features? So let's look at the answer. So the answer has been proposed in a research paper. So node edge disentanglement, variational autoencoder, published in 2020. And actually the solution is very simple and very intuitive. So what do we have here, guys? Let's look at this together. So we have the input feature matrix, the graph topology encoded in the A matrix, and the edge feature tensor. So here we're using the tensor, and the goal is to generate F prime, G prime, and E prime. So if we're doing this in a supervised way, which means we're having, so here in this example, you can have a target graph. So this would be a different target graph, and you can have also the same graph if you're doing self-reconstruction. So this is supervised learning, and this is self-supervised learning. Okay, so you can have this work on different scenarios depending on the loss. If you want self-reconstruction, you do G minus G tilde, right? So this is, let's write it here, G minus G tilde, the same graph. And for this one, you do G target minus G tilde, right? So the target graph from the input. So in this one will be, of course, expressed as a function of some, the original graph and some set of parameters theta, okay, including encoder, decoder. This is the total transformation that includes the encoder and decoder transformations, right? So it includes F encode and also F decode. All right, so now here it's actually very simple. So first you have a node encoder. So giving the features, we learn how to embed them. So we learn how to embed the F. Given the edges, the adjacency, the edge and the features together, we learned how to embed the graph itself. So this is the topology, this is the A matrix, right? And here, giving the edge alone features, we learn how to embed the edge features into ZE. So here, we're learning three representations. One of, how to embed the feature vector of the graph, a single embedding of the graph itself, the topology, which is the adjacency, and an embedding of the edge attributes of the whole graph. So the graph is, so these guys are collapsed onto a single vector. And here, this is the vector that embeds this whole matrix. This is the vector that embeds this whole tensor. And this is the vector that embeds this whole graph. And we have seen using GCN, we can embed graphs, okay? Now, one thing to learn here is that we want to learn also the distribution of the Z. So ZF will be drawn or sampled from a particular distribution. So the green one here, so let's do green. So this is sampled from a distribution with, you know, like a mean mu F and then standard deviation sigma F. And these are learnable. So we want to learn these two. So these are learnable hyperparameters. Now for the, you know, the Z is the same here. So it's, you know, ZG for the graph is sampled from mu G sigma G, right? And then the last one, which is this one, is sampled from a distribution of, you know, mean mu E and sigma E. All right. So these are all hyperparameters that we want to learn. So learnable hyperparameters, it kind of increases the dimensionality of the problem. But yeah, so we want to learn these. And once we learn them, we learn the distribution of each, and then we can easily sample. So once we learn these, we get the embeddings. And then for generating new samples, it's very simple. We pass these through the decoder, right? So the node decoder and the edge decoder, and we can get easily the E prime, F prime, and we can reconstruct the graph using these two, using the decoder function. So we have here the Q-phi, as we have seen before. These are our encoding functions, right? And then these are the decoder functions. And then we can produce the decoded network according to the Z. Now, very easily, if you sample from these distributions, so how can we create new samples? You just need to sample from these distributions. So, and if I randomly sample, so let me write it down. Let's write it down. So if I sample a new ZF sampled from N mu F sigma F, right? And I pass this through the decoder, the P theta, right? We're gonna get a new graph. So, and same here for ZG and ZE. So we sample from their respective distributions and we pass them through the edge decoder, and we're gonna get the E, pass them through the node decoder, and we're gonna get basically the node features, right? So that's how it works here. It's actually very simple. You guys can also write it down neatly. Shouldn't be difficult.